Alright, so now let us move on. The next module that we will look at is absorbing boundary conditions. Okay. So, we are putting together all the building blocks. First we looked at update equations, space and time, how do we update. Then we put a material inside, how do we handle a realistic material. Next thing is we need to terminate our computational boundary somewhere, how do we terminate it, right. So, absorbing boundary conditions. These absorbing boundary conditions are the same as what we studied in the case of FEM, okay. But now we have to put it in the language of FDTD, okay. So, a little bit of this will be more like revision for those of you who have seen the FEM module, okay. So, absorbing boundary conditions in general, okay. So, they come in, so we will call them ABCs, absorbing boundary conditions, okay. They come in 3 varieties, and this is true of CEM, not just FDTD, okay. So, this is CEM in general. Okay. So, let us say that this is the computational boundary, okay, omega, I mean gamma. So, the first variety is what would be called a local ABC. So, what is the meaning of a local ABC? Means that the value of, I mean the way I implement the boundary condition at say this part of the boundary depends on only the local values of the field. It does not depend on anything else, okay. So, the word itself suggests local ABC. So, you saw that for example, in your FEM, the spatial derivative dE by dx was replaced by jke. So, the value of the field at that point only, not anywhere else, right. That is the simplest way to implement it. The second is a global ABC, which means that to implement this boundary condition, I need to know the value of all the fields on the boundary, and actually you have already seen this. In the case of the integral equation method, when you write a contour integral on the boundary, that one equation involves all the fields along the contour. So, that's also a boundary condition, because you are imposing it only on the boundary, but that is a global boundary condition, it depends on all of this, right. And the third, which is actually very popular in commercial software and all, these are called absorbing media. Okay. So, the most popular of this is what is called PML, perfectly matched layers, which we will cover. So, here the philosophy is that you add another material over here, which has an absorbing property, okay. So, I have to design this material, which basically absorbs the wave and does not send it back. So, no numerical reflection, okay. These are the 3 things. So, what we will look, so we have actually seen local ABCs in FEM, we have seen global ABCs in integral equation methods, and we will look at absorbing media a little bit later, but the simplest ABC to implement is obviously local ABC, this guy. So, we will once again implement this local ABC in FDTD, okay, and then we will go to absorbing media. So, a few historical names over here. So, Engquist and Mazda, they are their names. Engquist, I never get the spelling right. Engquist and Mazda. So, these guys are the scientists who gave the first and second order ABCs in the CEM literature, okay. So, this is way back 1977, right. And then you had a person by the name of Muir, applied it to FDTD for the first time in 1981, okay. So, FDTD is not that old a method also, it is only I mean, it needed a upgrade in computing power to become popular, right? So it's last 30 years that it has been used. Okay, and since then it has been developed more and more in sophisticated ways. Okay, so as before, when we looked at this local ABC in the case of FEM, what did we do? We had looked at the wave equation, right? So we'll again go back to our usual wave equation. And we know that the solutions to this are of the form e to the j kx plus minus omega t. Yeah, we all know this is just revision. Now, let me try to write this equation or interpret this in a different way. Okay. Supposing I write this equation as in the following way, in terms of first order derivatives. So, equation 1 was satisfied by both the solutions, left going and right going wave, right. What about equations 2 and equations 3? Do they also satisfy both left and right wave? No, right. So, supposing I take the first equation, what E satisfies this? Right going wave, right. Supposing I take e to the j kx minus omega t. The first derivative gives me a plus jk, the second derivative gives me a minus omega by c, j omega by c, and omega is equal to ck. So, I get it is satisfied, right. So, this is satisfied, and the second equation gives me E is equal to j kx plus omega t, okay. But they do not satisfy the other equation. Okay. So, remember how we had derived the this wave equation, I mean the absorbing boundary condition in FEM. We had taken a plane wave traveling in a certain direction, and we had asked what is the condition satisfied by this wave equation, what was the relation between the spatial derivatives, and we had imposed that at the boundary. We are saying that it should hold true for a wave traveling in vacuum. We will force it on waves traveling in any direction, and we will suffer some error because of that. So, same philosophy is going to be used now. Let us say at a right hand side boundary, okay, of a computational medium. So, right hand side boundary. Okay, so there is, let us say, computational domain like this, and this is my boundary over here. Okay, so boundary, and a wave travels like this, and I impose the condition, this one. If I impose this condition and there is actually only vacuum over there, then a right traveling wave, will it see any numerical reflection? Here is a wave traveling like this. So, how is it traveling? It is traveling on the E grid, FDTD, it is updating every time I am updating, moving the fields, let us say in space and time. Now, it hits this boundary and there is no computational domain to the right. So, I need to impose some boundary condition, and I impose this boundary condition. Is that a good thing? Yeah, but this is the rightmost boundary. At the rightmost boundary, so there the scatterers are always to the left of this boundary. So, what will happen here? Trivially good, right? If it is a 1D problem, there is absolutely no issue over here, because this is a perfect boundary condition, right? So, this is perfect for, and that was also the case in FEM. In a 1D problem, it was perfect. there is going to be no reflection because this is always true.